exclusion principle and Huns Rule and stuff like that, okay? So first, the idea is that, you know, our periodic table has this organization to it, right? That is kind of somewhat arbitrary, right? And that your rings, like you've known it to be your rings in your atom, right? Oh. So like you had your, you know, your inner shell that can hold 2 electrons, and then your next shell that can hold 8 electrons, right? Oh, sorry, that's 2. And they even, you know, you even got used to this, grouping them together in 2s when you wrote in the 8, right? So, okay, so let's kind of like give Bohr the credit for saying that there are these kind of like principal, fundamental sort of like levels of energy away from the nucleus. So as we go further away, we have to think about the electrostatic energy. Okay, so let's imagine that we bring the electron from here to here. Are we bringing it closer to what it wants to be close to, or are we bringing it further from what it wants to be close to? That's an electron, and we're pulling it away from the nucleus. The nucleus is a positive charge, right? So that is a positive charge. That is a negative charge. And if we're going to bring a negative away from a positive, is that going to take energy or is that going to give us energy? Like it's going to require the investment of energy, right? Okay. So what this means is like, you know, these energy levels, like the sort of closest, you know, spotting and noticing that they always stay this distance away and they kind of dance around the nucleus at that distance, we call that the first energy level. Okay. And what's that? Sorry. Yeah, exactly. That's the sphere. Okay. But Bohr thought and kind of like was able to show, at least initially, that there's just a bunch of spheres like an onion, right? Like sphere on sphere on sphere, and it's like layers of sphere, and I can kind of just keep doing this, right? Well, it turns out there are better ways to organize around the nucleus than spheres on spheres on spheres on spheres, okay? So, and this is just a consequence of kind of like something that we found, okay? Initially, if you're going to put 2 electrons together, then it is okay to put them in a sphere, okay? And in fact, the next 2 electrons that you put in, they can go in a sphere, okay? But then it is lower energy. So the whole idea here is that these electrons are naturally going to fall to their lowest energy that they're allowed to be in, right? Like you're telling me that it would be an investment of energy to get it to go up here, right? So it's kind of like saying all water falls downhill, right? Like if you can expel some energy, then the water is going to go down into the valley, right? Well, you can think of it as the same way. The electrons are going to travel kind of like closer and closer, as close as they can, to the nucleus if there's a spot for them, okay? So that means they're going to go down the energy hill, right? Okay. We've already kind of done a little bit of the work that we need to talk about kind of organizing this graph here. So what I'm going to do is I'm going to like rotate my head so that the green arrow is this green arrow. This is the same green arrow, right? So that the energy as you go away from the nucleus, that there represents that kind of energy as you go away. Okay? Can you picture that? That is the same green arrow as this green arrow? Okay. The orange line, I'm just sort of like trying to make it look like it's just like level, like this looks like now just sort of like 1 level and then 2 levels, right? And like this is the nucleus. Are you with me on that? Okay. And so what Bohr found was that there are kind of these two shells, and I can, I can fit 2 electrons here, and I can fit 8 electrons here, and he didn't really know why, okay? And I don't actually think the 8 was attributed to Bohr, but let's just say that Bohr got it to sort of jump up in a level, okay? And got it to jump down in a level, okay? So can I ask how he got it, how he was able to do that? Do you know? We have to, what, give it energy or take energy away to get it to move up? Yeah, so what we do is we shine some light on it. HF represents some light. Yeah, no problem. Okay. So this will absorb. This will absorb light. Okay. And an electron will jump up for a second. And then it will give off some energy. And so it will emit light as it goes back down. Okay? So this is something that we'll talk about later once we get more comfortable with this system. It's called the emission and the absorption spectrum. You might have talked about it already. I think that's maybe like the Yeah? Mm-hmm. Yes. So I can actually get it to jump up to the 3rd level. Okay. And that's going to represent, that's going to be a different jump of energy. Like this is actually a proportional sort of idea, right? And it's only going to work that if you have the exact, because like this is a scale. Like let's say, for example, this is 100, this is like 200, and this is like 180. So if your gap is 80, then you're going to go to n equals 2. If your gap is, or if the energy that you give it is 100, then you're going to go up to n equals 3. Okay? We don't have to be super precise about that. We will more later, but yes, you're right that it's kind of like, if you give it more energy, then it will kind of like, the color will change. And yeah, more energy, right? Because violet is at the far end, right? Versus like orange and red, which is like lower bits of energy. Okay, so and we'll get better there. Okay. So that was kind of like, pretty much your idea from like grade 9 and 10-ish, right? Was we did these shells, yeah? Okay. So it turns out, we kind of have to zoom in, okay? So in the world where we saw n equals 1, there is actually only like a thin layer there, okay? So the reason that we can only fit 2 is because it turns out that there is just one configuration that it could be in, okay? The n equals 1 is the same as that number there, the 1 there, right? You've comfortable with that when I say like 2s. Okay. Yeah? No. Yeah, okay, so let me answer this question. Yeah, it's a good question, right? So this is what they actually found, okay? So you would have suspected, right, that if it was like 2 and 8, then, and okay, so maybe, it's believable that you kind of have to do this. So what does that mean when I do that? Yes. All right, just one of those is 1 electron. But then why are they in opposite directions? And why do they kind of look like arrows? Okay. Okay. Yeah, yes, we'll talk about it in a second. Okay, so the important part there is that electrons are basically like these kind of like spinning balls that have negativity on them, right? And because, we approximate them as spinning, right? We sort of say they're spinning randomly in space. Yeah? Well, go back to your magnetism unit. That is a charge moving in a clockwise direction. What does my thumb represent? magnetic field. So spinning electrons are moving charges. What's that? Sorry. Yeah. Right. Yeah, for sure. This is physics. Like this section is physics of chemistry. Yeah, you can't escape it. But it means that you can handle the physics in chemistry a lot easier because you've done the hard stuff, right? Okay, so spinning electrons are moving charges which create a magnetic field. Okay, so what that means is your partner in your... So this one will actually be down, okay? Because, you know, you don't have to know this, but it's the right-hand rule, but because it's electron, it's the opposite direction, so it's down, okay? But what that means is that there's some like force kind of in the up-down direction. My neighbor actually in my... So this little platform is called an orbital, right? You've probably already seen this, but each platform... Yes, each platform is an orbital. Yeah. Okay, good question. So 2 electrons can fit in 1 orbital together. Okay. The reason that it's 2 fitting together is because there's going to be one that's spinning in one direction to give an up arrow, and then the other one is going to give the exact opposite down arrow, and together they cancel each other out. Okay? Together they cancel each other out because it's up and down. So the magnetic fields, up and down. So they cancel each other out, right? So, and in fact, magnetism, like what you and I know as magnets and materials that can be magnetized, comes from an electron that doesn't have a pair. So it's a lonely electron. If I could get to this scenario, then that means I could have 3 arrows working together to create a magnetism in that upward direction. Now that whole atom has a magnetism to it, and that's what iron is. Iron looks like this. Okay, so we're getting a lot closer to sort of like being able to tell how the world is around us. This is a lot closer to the truth than anything we've told you before, at least. Okay, still not perfect truth, but it's a lot better. Okay, so each platform is called an orbital. Okay, let's get to what the sort of S and the P represent. Okay, but as I go throughout the S and the P and the D and stuff, every platform is going to get 2 electrons, right? But the way that I'm going to fill it is like the way that you saw me fill it here. So if I have equal platforms, then instead of pairing up and leaving an empty platform, these are still electrons. These are still electrons that hate each other, right? So remember, vertical height in this world represents what? This is called an off-bow diagram, or an energy level diagram. And the scale on the left side is energy. So the same height means same energy. Okay? So to the electron, if you're the next electron to come in, your choice is, if there's one electron there, your choice is to be a down in that one, or to be an up in this one. Which one would you prefer? If you're an electron and that other green one there is an electron already, would you rather be by yourself or would you rather be with another electron? Yeah. So this is one of the rules. We're going to go through it, okay? But I just want to give you some intuition, some story behind these electrons. so that you can kind of like use your intuition about what they want to do to be able to tell how they're going to fill things, okay? This is also going to be the explanation for why they do some weird things, because it's going to be your job you're actually going to be asked about the exceptions, because they're great explainers as to what the electrons care about and why they're making their decisions. There's some weird exceptions where like, oh, okay, it's actually like, it's okay to double up or some things like that when the energy jump is not that high. So your electron is never going to do this. So now, let's say you're an electron there. If the next electron is going to come in, are you going to go there or are you going to go here? Are you going to go by yourself or are you going to go double up? Okay, but this is so close to the last one. So why is it a different answer? Why do we double up here when we could be by ourselves? Yeah, so like you can kind of think of it like this, like, yeah, that is right there, but because there's an electron in it, right? Like when there's no electron in it, it's at that energy level, right? And then when there's an electron in it, now the next electron sees it as a little bit elevated, right? But now whose height is greater? Well, it's still this one, so I'll still go there, right? Now, when we do that with the first one here, we see them all as equal. The first one just says, okay, I'll choose this one. And now that one's slightly elevated. So now it makes sense that you would fit in here next. And now that one's slightly elevated. So it will fill in here, right? And now all three of them are equal. So now what's the next electron going to do? Any one, right? It's going to double up, right? Because they're all equal, right? Okay. So this is how we fill things. We fill them singly before we fill them doubly, but they have to be the same energy level, okay? And so like, make sure you're evaluating kind of like what heights are they at. They have to be at the same height for that rule to apply, okay? And you already did, like you did it well to say, no, they're going to double up in this case because this is, you know, because that's lower, right? Okay, so... And I'll put a name, like what we're basically doing is going through the Paulie exclusion principle, Huns rule, and the off-bow principle. We're just not putting names to them. So we'll put names to them in a bit. And it's I mean, you just have to memorize who's who. It's not like they make any sense. They're just named after the people. Okay, so you got to do that work on your own. Okay, so each platform is called an orbital. Okay, now let's get back to sort of like, okay, you know, why have you created this big crazy system? Well, because the n equals 1, the n equals 2, n equals 3 is not enough. You actually have to zoom in a little more, okay? So what I want to do is I kind of want to like exaggerate, you know, like this is usually how you're going to see it, kind of like nice evenly spaced things. But I want you to sort of see where these are coming from, okay? So imagine that those look like that, and they are at that level, right? And this one looks like this, and it's at this level, right? Well, if you're now Bohr, like trying to sort of like look at these tiny little things, you're just going to see n equals 1 and n equals 2. And for some reason, this one's going to fit 8, and you're not really going to know why, okay? So the n number is kind of like this, you know, principle. It's the first number that kind of matters in terms of what level you're in. And then in each level, there are some sub-levels, okay? So in the level 2, there is the 2s, and then there's also the 2p's. There's 3 2p's, okay? The n values from old days, yeah. Yeah. Exactly. Yep. And in fact, that's our first principal number, n, right? That's the same n as back in the day, okay? Like the first shell, second shell, third shell, okay? And it's generally pretty easy because each one is named with the principal quantum number in their name. So this is 2s, and the principal quantum number, that's what we call n, is the principal quantum number. That number is 2, and the 1s, the number is 1. right? So they're named after it, so it's helpful. Okay? Okay. Basically, like, you know, part of you're gonna have, and it's natural to have the question of like, why does this, like, what's going on? A lot of chemistry is investigating and then trying to come up with a reason for why, because that's the way it is. That's what we see, right? Like, we're not really responsible for the why. We're responsible for just looking at what's happening and then saying, oh, it's because of the electrons and the protons, that's why it's doing it, right? Like that kind of thing. So there's a strong feel of that in this world. Okay, so you got to bear with me, and then you'll believe me that it's kind of like been there, the whole system, the whole time, with the periodic table thing. Like the periodic table thing does bring a lot of this together. Okay. Okay, so the S and the P. Let's talk about what the S and the P kind of like matter for and what they mean. Okay. S, I mean, you can see S, or you think of S as sphere. Okay. So when we say S, we're talking about an electron cloud that looks like a sphere. Okay? An electron, and I'm going to call it an electron probability cloud. Have you talked about these? Okay. So let's kind of like explain that. But let's just say that it's shaped like a sphere. Okay. And the P's, there's only one sphere. Okay. There's only one. But these are like kind of like dumbbells. Right? You've seen this, and there are 3 of them. Yeah. And so they have this sort of like, you know, like ball or balloon on either side of a kind of like not so filled in middle, right? And where is the nucleus in this world? Yeah, exactly. Okay. Yeah, it is an hourglass. Yeah, you can call it an hourglass shape, right? So actually, when you do this with balloons, balloons behave almost exactly like this, okay? Because what this is about, well, actually, there's a better use in a second. Like once we sort of talk about how these things look when they're bonding, not just on their own, but when they're bonding, balloons really do what they do when they're bonding, okay? But this is an electron probability cloud that's shaped not like a sphere, but it's shaped like a dumbbell, okay? Okay. What in the heck is a probability cloud? Okay, so let's talk about that. No, these are orbitals. These are types of orbitals. Good question. Types of orbitals. And remember, orbitals hold. Yeah. Yeah. Okay. The sphere would have 2. It could have 1 in it. It could be like a hydrogen, right? That only has 1. And then, but then helium it has 2 in the 1s. And so it has 2 in that sphere, right? But then it has none in the 2s, right? So, okay. Okay, so let's talk about probability density, or you will hear me say probability density or probability cloud, okay? So let's imagine that you okay, wait, no, sorry. Before we start, let's just say that we've done our absolute best to try to take pictures of the electron, to try to get a picture of the electron doing its thing and dancing around the atom, because surely it's not a perfect like ring, right? And surely these electrons are kind of like, they're moving fast and doing some craziness, right? So we tried our absolute best to figure out where the electron is. And in fact, it turns out that you can't ever really prove exactly with 100% certainty where it is. Okay? Because, and this is I don't know if you've heard about this, or maybe you know about like Breaking Bad, but this is now more of a fun fact because of Breaking Bad. But the Heisenberg uncertainty principle says, and is kind of the judgment on this, that we'll never exactly know for sure where the electron is and how fast it's moving. Okay? You can know more and more where it is, but then you know less and less about how fast it's moving. Okay? And so you kind of have to accept a little bit of error in both of those. Okay? What that means is you don't exactly know where the electron is. So what you're going to do to figure out kind of like how is the electron hanging around the atom, what we want to try to do is sort of draw the space that the electron occupies. We want to sort of like trace the path of the electron. Okay? So imagine that we gave the electron like a smoke, like, you know, those like skydivers that put smokes on their feet and you can like see the smoke in the air. You've ever seen that before? But can you imagine it like a jet plane that has the like colored smoke at the back, you know? Imagine a small version of that. It's just like a little, or like, you know, a photo shoot. Sometimes now they do it in photo shoots. My brother had one of these for his wedding where they had like a cool white colored like smoke bomb that they just like, you've seen those? Okay, there you go. Yeah. Okay, pretty good. Yeah, exactly. So let's imagine we have one of those and we put it on the electron and we let the electron do its thing and move on its path. What we will start to see in the smoke is a dumbbell shape when it's in this orbital and a sphere shape when it's in this orbital. Okay, so the probability cloud or the probability density is where you'll find the electron 99% of the time. Okay? So 99% of the time you'll find it either in that like big blob or in that big blob. Okay? And in fact, you can kind of take like any chunk. Oh, that doesn't really work when I do that, but let's just say, you know, I take like this chunk of the dumbbell and let's say that represents 5% of the full probability density. I will find the electron in there 5% of the time, okay? But I can't really ever say that it's like exactly here or it's exactly there. So we have to deal with these kind of like, okay, 99% of the time it's in this shape, it's in this shape, it's in this shape, okay? But what that also means, you know, technically this is more for like a communication question. Technically the electron could be anywhere in the universe. Okay? Okay? Gotta love physics, right? Like, no, even way less than that. Like, you know, like if 99% of the electron distribution, 99% of the time it's in this little area, then it's such a tiny percent when it's in like Timbuktu and when it's in Arizona. Like, you know, there's going to be tiny little percentages there. But technically there is. Okay. So what we do is we kind of stop the border of the sphere at 99%. Okay. Okay. So what we see is we end up seeing first that in the n equals 1, we only have the s. When we get to n equals 2, when we get to the second shell, we access a new layer of subshells. Or sorry, yeah, these are called subshells. Okay, so subshells. And then these are orbitals. Okay. So this is the shell. So we can say the shell number for the principal number. Okay. And okay, so orientation, what orientation means, what that word means outside of science or like in science too, is how am I, what direction am I facing relative to you? So right now I'm oriented towards the camera. Right now I'm oriented towards the door. Right now I'm oriented towards the window, right? Like that's it, that's all it kind of means. So orientation, I think, is spin up or spin down. That's what I think it means. Yeah. Mm-hmm. No. What? Huh. Yeah. Yeah. Wait, are you thinking configuration? Is it configuration? Electron configuration? Okay. So electron configuration is kind of like this whole, it's the name for this whole unit, and that's what we're building towards. Okay. So I'll tell you when we get there, like this is, I'll be able to say what's the electron orientation of this, and you'll know what I mean. Okay. Or sorry, the electron configuration. You've got me saying orientation. Sorry. Okay. I don't, in this world, I don't think that there's like a formal definition for orientation. Okay. Your teacher might have accidentally been saying orientation and thinking configuration. Okay. So we'll talk about it, but configuration is for sure in this unit. It means something. Orientation, both. I could like this. What I'm doing is giving you an off-bow diagram of the electron configuration. But I could give you the short form, and you soon will know exactly how to turn it into this, and they'll be pretty equivalent for you. Okay. So, okay, good. I'm glad you kind of like asked that, because that was important. And to have that in your head when it's like, not anywhere is tough too, right? Or like it sounds like it's configuration, and your teacher might have maybe been saying orientation. Okay. 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 So the rule basically is that you sort of access a new one every time you go down a shell, right? So in the threes, we have a sphere as the innermost layer. And then there are three of these dumbbells. So there's one that's in the Y direction, one that's in the X direction, and then one that's in the Z direction. You could picture it. And that's why there are three of them. Well, if it's P, right? Because remember, P is what determines if there's three of them. And P shows up in many places. There's going to be a P here as well, right? Mm-hmm. Yeah. Yeah, exactly. Yep. Yeah, for sure. Exactly. Yeah. So I could ask you about one of the three P subshells, right? Or one of the three. So these are the three orbitals of the P subshell. Yeah. That's right. Yeah. Okay. Cool. Okay. So we do have to access that new layer. So what comes after P? It's D. And D has some funky shapes. Okay. So I don't know where your teacher stands on memorizing the shapes. Do you know? Okay. So they're all like mathematically equivalent, but they don't look as equivalent as these ones do. Okay. So the D, there's no uniform shape. So there's no single shape, let's say. Okay. But there are 5 of them. Okay. So basically it looks like a lot of them, or 4 of them, look like a double dumbbell. Right? And in fact, 3 of them kind of go in between the axes that they're on. So that is called the XY version, right? Because it goes in between the X and the Y, right? And then there's an XZ version. And then there's a YZ version, and it goes in between each of those. Okay? So there are 3 of these. And then there's one of them that is actually lined up on the actual axes. Okay, so there's one like this. Okay. And then there's one that looks nothing like any of the others. It's got a donut in the middle, and then it's got our normal lobe-looking type things. So, in fact, actually in third year, in third year calculus, we derive these shapes. We come up with these shapes. So, so like we can, if you want to, talk about it, but basically it's like you have a certain graph and you spin it around the center like this, and you end up with this shape. Okay? That's the best I can give you. Okay? But energetically, in terms of, you know, how much energy the electron has when it's in each of these orbitals, they're the same. They're considered the same. So these are 5 equal energy orbitals. And that's ultimately what matters. Okay? Okay. Let's also just say that there is an F category. Okay? And those ones are even weirder and uglier, and there are 7 of them. Okay? Okay. And that is all that matters there, is that it's 7 equal energy orbitals. That's all we'll ask you to do, is sort of come up with your 7 steps, right? Your 1, 2, 3, 4, 5, 6, 7. Yeah? Sure. Uh-huh. 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 Yeah. Yeah. Okay, so let's build it. Let's build it. So that I want to make that, like, your indecision there, I want to make that like hard to find even. Like the periodic table is like you can read it off almost directly what the electron configuration is. Okay? Okay, we're pretty much ready now to just start doing electron configurations. Okay? So I'm going to do the off bow and then the shortened or the shorthand of a couple. Okay? So yeah. Okay, so who would this be if it looked like this? What would that be? Oxygen. Yeah, this is neutral oxygen, right? Awesome. So neutral oxygen. And the shorthand is going to be, do you want to try it? We write it like this. So that tells me how many electrons are in that orbital. Actually, that subshell. So 2s, how many? Yeah. And then 2p, how many? Yeah. Is it enough to just say 4? Like, will I be able to tell that the electrons will look like that in their 4? Will I be able to tell that every single time? Or could it be that they will maybe sometimes look like, you know, this? And I have to specify. Well, this would be a violation, right? So that is the question, right? Like, as long as you're not violating anything, then you're okay with that, right? So check for those violations. That's the hardest one, is like when they're equal energy and you accidentally double them up. Okay, the other ones are pretty easy. Like, you'll be able to tell when, like, I do this kind of thing, right? Like, oh wait, why are those up there when there's an empty one down there? Okay. Cool. So yeah, that's the shorthand. Okay. So all you do is you sort of just tell me how many there are. And then with my knowledge of how they fill in, I should be able to come up with the configuration. Okay. Okay. So, okay. So there's that shorthand. There's also another shorthand, because every time, every full shell can be or can be like displayed as a noble gas, right? So I could really say helium 2s2 2p4. And what am I saying? I'm saying the electron configuration of helium, which is 1s2, and then on top of that 2s2 2p4. So this is another shorthand. This is called the noble gas shorthand. Have you done these yet or seen these? No. Okay. But okay, that's okay. I think you'll get there, or if not, he'll kind of like try to sneak this in somewhere. It's a pretty sort of like simple addition that if you have a bunch of full layers, so let's say for example I had, you know, I had like 1s2, oh sorry, 1s2 and 2s2 and 2p6 and 3s2 and 3p3, right? So first of all, maybe can you tell me who this is? Who is this? Which neutral atom has this electron configuration? Who is it? Okay, this is the thing. This is what I want to talk about the periodic table for now, because this, I want to make this an automatic thing. Okay, so let's get our image of our periodic table. Let's just grab you. See if this works. Did that work? No, it's disappearing for some reason. Okay. Copy. Did that work? Oh, it's trying. What's going on? Okay, sorry, just one sec. Maybe it's still trying to paste the other one. I don't know. What? Okay, sorry, just one second. Okay, I just want to get something that's kind of nice for us to work with. Yes. Will this work? Hey, okay. Okay. So, remember that, you know, number of electrons, oftentimes, especially when you're talking about a neutral atom, is the atomic number too, right? So, this has one proton, and neutral, it has one electron, right? Okay, so in fact, can I put the helium, like, helium should actually, it's better fitting over here. Yeah? Okay. The reason is because, and there's also a reason, and we'll talk about it, why it's over here. But the reason I want to put it here is because what we do is we will jump to a new level when we get to a new N value when we get to a new shell. So every letter here represents a shell, right? Or every level, sorry, right? Okay. And initially, you have just 2 electrons, right? Before you have to start a new level, right? So that there, that represents the first electron that would go into the 1s. So the way we label these, we can if we want, 2px, 2p, well, we can say xyz. Okay. And we can label each of them that, or we can just call them all 2p. Okay. Okay, but if it was helium, then this is what it would look like, right? And then if it was, oh, sorry, no, if that would be hydrogen, right? That was a test. Okay. If it was helium, it would fill in the second electron into the 1s, and then that would be a full valence shell, right? So that is why helium is a noble gas, because these are all full shells, right? Okay, so that is the 1s spot, those two. And then what do? We go to the next level. And so lithium will look like this. And then beryllium will fill in the second electron. So those two there represent 2s. And then what's after 2s? Yeah, and how many fit into 2p? Yeah, right? 2 there, 2 there, 2 there. It's a total of 6. So this is the 2p. Right? Yeah. So really, once you kind of like know where you need to look, so this is the 3. What? Yes. What about this? Good. And so when we say 2p6, we're talking about neon, right? And when we talk about 3p6, that means that we have all of the electrons in the 3p. That means we're argon. Okay? Yeah. Okay, so let's get to it. So the electron configuration or the periodic table tells us this is an exception to the rule. Okay? This is an exception to the rule where basically, so let me kind of like draw the extension of this and see if I can make it believable. Okay, so 1, and then the P's are over here, and then the D's are here. Yeah? But then the 4s is here. So if you're an electron trying to find the lowest spot on the hill, right? Well, this is where we can kind of like understand. So this is an important exception to talk about. I don't know if I want to talk about like every little detail of this exception. I just want to introduce you to the idea that as I'm filling electrons here, so I'm going to put this one in here, put this one in here, then go here, then where? Good, yes, and then the next one here, right? And then they're going to double up, okay? And then I fill like this, and then I double, and then I go here, and I go here, and I go here, and here, and here, and here. And now, these are basically the exact same height, okay? They're almost the exact same height. But as an electron, this is something we haven't quite talked about yet, okay? But we have gotten a hint to it. there is some extra stability, some extra, on top of everything we've been talking about, some extra stability from having a full, a half full, or an empty shell. Okay? So it's kind of like, you know, all 5 of these can work together, and that's nice. Versus, so close. We were all almost the same energy, and we were all almost like in synergy, but okay, like, of course, I'm just giving you a qualitative way, a sort of living way to think of these electrons, right? But that's the idea, that they get much, much happier by being full or half full. Yeah. What? So he was full. He was trying to say that he was content to be full. He was complete. Oh my god. Yeah. Oh my god. What a way to show that idea. I've never heard that. I've never heard that description. That's pretty crazy. Yeah, you just kind of like, okay, yeah, got it. Thanks. Okay, so that's an important one. So that one that we just said is called Huns Rule. Okay. The Paulie exclusion principle is the one that says basically like every electron has a unique address and you can only really have like up and down in the same orbital. Otherwise, it's got to be a different orbital. Okay. And then the off-bow principle is basically the one that says like fill them up from the bottom up. Okay. So, you know, we can if we want to, like, but it really, once you read them, you'll be able to tell who's who and how we've been working. Okay. But this new rule, it's called Huns Rule, if you want to know. But if not, it's just about half filled, filled, or empty shells. Okay. So now you have a choice if you're going to be the next electron. Do you want this, the one on the left? Oh, God. If this works. Yeah, okay. Thought I screwed that up. Okay. So, oh no. I gotta close my program. Sometimes it gets too big and it starts to act all funky. Okay. So, do you want to be the one on the left, or would you prefer to be the one on the right? What do you think? Because that's... Why? Yes. Yes. Okay. So can we just say, so also this is now where the where this notation is going to save us. Okay. Because if I had to, then I would write the shorthand of this as 1s2. Can you take it from here? Mm-hmm. Yep. Beautiful. Beautiful. Yeah, you do have to put the 1, okay? Okay, good. So this is who? Who is this? This is potassium. Yeah? So that is the 4s, right? Okay, so this is potassium, right? And neutral potassium. Okay. Good. Yes, I want to go through I want to go through this whole row now and look at their electron configurations and see this choice, see this exception, see this thing happening. This weird thing of why the d orbital is there, okay? So first of all, I mean, maybe this is enough now for you to believe why the 4s is before the 3d. Right? Like, they just happen to be that close. And for an electron, it's better to be in the s because it means you get that extra stability of the full or half full. Okay? Okay. So let's go to calcium. So, okay, wait. So, sorry. What I was saying was this is where it's nice now to do this notation so that I don't have to give you all of the full inner shells, right? These are all just full. Yeah. Yes, exactly. So you put the full inner shells and then you just show me the valence, right? So here, how come I didn't just put 2p4? How come the 2s2 is there as well? What determines valence? What makes the decision on valence or not? For all of them. It's not about the last subshell you're in. It's not outer subshell, right? Valence was an idea we taught you in grade 9 and grade 10 when you thought the world looked like this, right? So it's only about the outer shell. So it's the whole shell, though. So anything with a 2 has to be included. Because the 2 is the valence shell. Does that make sense? 2 is the valence shell, right? 2 is the outermost shell in this one, right? And so anything with a 2 in it has to be included. So we don't just include the outermost 2 thing, right? And skip the 2s2 because the 2s2 is just as much of a part of it, okay? Electrons in the valence shell. Yeah, good. Yes, exactly. Okay. Okay, so now here, this is nice because now I can just say argon and then say 4s1, and I'm saying the same thing. Okay? Okay, so that's calcium, or sorry, that's potassium. Can you tell me what calcium looks like? Argon again, and then, right? Because we're sort of saying that it looks the same, but it has one more electron. So these don't really get touched, right? Because those are the inner shells. Because we're just saying the inner shells are still there, and argon is what only the noble gas that's last, because these ones represent full shells. So the argon is like everything but the valence shell is argon, right? And those are all the full inner shells, and that's argon. Right? And so 4s1, it's the only one, right? Like it's always the last one up and right up to the valence shell, if that makes sense. Yeah. Yeah, exactly. Yeah. Yeah, good question. Yeah. And that's an awesome way to like check your understanding is to like, okay, let me extend it to this scenario, see if it works, right? Awesome. Okay, so calcium then, we're saying still the full inner shells, but what does its valence shell look like? What does its valence shell look like? 4s2, beautiful. Okay. Now, what's next? Scandium. Yes. Okay, so I want to talk about these. So titanium, vanadium, chromium. And then manganese, iron, cobalt. Okay. Okay. We'll get there. So 4s2. Okay, so that looks like this, right? Beautiful. Okay, next one. Where does the next electron go in? Let's add one more. So it's still going to be argon, but then it's going to be... Well, what's after the 4s? Yes, 3d. Yes. Good. So that's the next choice, right? Like that's the next one available. So we have to start filling that one, right? For sure. Yeah, it's kind of like walk one more step every time you start a new shell, right? Like, okay, the first step is just S. Okay, now turn around, start a new shell. S again, and then But now I got to go to P. Okay, now start again. SPD. Okay, now start again. SPDF, right? That's exactly what it is. That's exactly what it is. But this is part of the exception. So this is part of the weird rules. But it is an explanation as to, wait, I thought we were in 4. Why is this 3, right? Like, that's maybe why you were sort of like, wait, what is with these d orbitals, right? Okay, cool. So yeah, it is weird, right? But this is actually the 3D, right? So this is the 4s. What is this here? Yes, nice, good. Because this is the 3p, right? So what about this? Yes, what about this? That's right. And then? Beautiful. And then? Good. And then? Not quite. Because this is something that we've sort of pretended to, or we've let slide the whole time. But what's that? It's the F's. Yeah, look, this is supposed to go to this column. Right? So that is why that's at the bottom there, because it's as if this thing opened up again, and it's as if we'd have another gap waiting for the F's the whole time, like we did waiting for the D's the whole time. So instead of doing that, we just throw it in there at the bottom. Okay? Why? Oh, okay, yeah. So there's some new, we have some new, like a bunch of these are probably just a bunch of U's in your thing, right? Yeah, we have some new ones. Yeah. Okay. So yeah, so after the 6S is the F's. Which one is the first F category? Think about your pattern, your S, SP, SPD, SPDF. Who has the first F? No, because 3 went to D and stopped at D. So then 4 goes to D and goes to F. 4 goes to F. So 4F. So that is the 4F way down there. Okay. And then this is the 5D and the 6P. Yeah? But at least now you can just read it off and you don't need to really know about the trick, the exception, because it tells you, hey, 4S is first, right? You're going to use the 4F first, and then you're going to go to the 5D. Because look at the numbers. 56, 57 to 71, and then 72, right? So make sure you follow the numbers. You have the same sort of look? Okay. Yeah, sometimes they do it well and sometimes they don't. Oh, what? I've never seen that before in my life. What is that? Okay. My God. I've been doing chemistry a long time. Never seen that before in my life. That's so funny. Okay. Okay, so after the 6P, then the 7S, and then what is this? What's next after the 7S? Same sort of thing. Yes, 5F. Yes, good catch. Good. 5F, and then 6D, and then 7P. Okay. Uh-huh. Yeah. Neither does the 6, actually. Right? Things get too big and unstable. Okay? Okay. So Okay, so back to this. So this is huge, right? Like that, being able to kind of just see now any atom in its spot and being able to kind of reel off its electron configuration is a big part of this unit, and it tells us a lot about your understanding too. We do still have to talk about quantum numbers, okay? But I think that'll be pretty easy now, okay? Because it's really just this system, but with numbers. What's that? This is quantum numbers, but without saying any of the numbers or talking about any of the symbols for the numbers. But it is the quantum numbers. So like N is the first quantum number, okay? S and P and D and F is the second quantum number, but it's not a number because they're S and P and D and F. Okay? Yeah. But no, sorry. In the quantum number model, they are numbers. But they mean S and P. Like 0 means S, 1 means P, 2 means D, 3 means F. Yes. Okay. And then, you know, the spin. We've talked about the spin, right? This is the last quantum number of plus a half or minus a half. That's what the spin number means. No, S is 0. S is 0. S is 0. P is 1, yeah. D is 2. And F is 3. This is your L number, right? Okay, we'll get there. We'll get there. But first, honestly, like the little amount that we have to do to like extend it to the quantum numbers isn't that much. That's why I'm not focusing on it. And it's really just, I don't know why we've come up with this like number system. It doesn't, I don't know, but you have to do it. We don't even use those quantum numbers any other time in any other, like I did, you know, biochem up to 5th year, and I never saw those quantum numbers again. All this other stuff, the electron configuration, all that's important, but the quantum numbers are just like a system that somebody was like, hey, this works with a little system I made, and now we have to teach it, okay? But, okay, so that's my little rant. Okay, so let's keep going, because there's going to be something funky that happens here, okay? And it's related to that decision that led to 4s being there in the first place, okay? So let's keep going. So we're at scandium right now, right? So let's add another one, titanium. Where's it going to go? There? Okay. Okay, so that's titanium. So that's 4s2. 4s2, 3d3. Oh, sorry, 2, right? 2. Okay. And what about the next one? For S2. Ah. Okay. So now, this is where we have to talk, okay? Because why did you fill the 4s in the first place? So you could fill it with the electrons, and that got you some extra stability, right? From being half filled or filled, right? Can you, and you couldn't do that with the d orbital, right? You only had 1 electron, so you put it in the s. And then you had 2 electrons, so you put it in the s, and now that's still a full one, right? So that's good. But now you have to work with, in front of you, 5 electrons. And that's enough to fill the d orbital, isn't it? So this is where we have to be ready for some funkiness, okay? It's actually not quite yet. Not quite yet, okay? They don't move for vanadium. They don't move for vanadium because the jump of 2 electrons is too much, okay? Because imagine it like this. Like one of these electrons is going to randomly be moving around, okay? And just be ready to sort of like think of it like a little popcorn kernel, kind of like every so often it's jumping up in electrons and then coming back down. And so that's a way that we can test that we're actually at the lowest energy, is like constantly like dislodge yourself and then go back to the lowest energy. If you return to where you were, then you were in the lowest energy, and that's good, right? And if you don't return to where you were, then that's also good because you were in the wrong configuration. We want to be in the lowest configuration, right? Okay. This is not where the electrons start to move, okay? This is where the electrons start to move. Okay? So this is okay. But this, well, I'm just going to do this. Cheat a little bit here. This is not okay. It would just be 3d5, but then would it still be 4s2? No. Instead, it would be argon 4s 1 3d5. That's a total of 6. That's a total of 6. Right? So this is, instead of doing this, because this, on top of liking filled and half filled and empty, they also get really, really eager and can really convince electrons to do some weird things when they're really close to being full. Okay? So this is why things like fluorine is such a reactive molecule, because it's really, really close. It's one electron away from being full and being happy. And so when you're one electron away from these things, you can convince your partner orbitals to do some crazy things. And in fact, that 4s is still happy because it's half filled and you get stability from being half filled, right? So it's okay. So that 4s is okay with it. And remember, the energy jump here is pretty tiny, right? So this is almost like us saying, hey, there's this new energy level that has 6 and you're trying to tell me that it does this? Right? Like that's basically what 3d4 and 4s2 would look like. But that's not how electrons behave. When they have equal energy orbitals, they will split, right? And so we'll see that electron move over there. Okay? Okay, so that's the exception that you kind of have to be ready for. Okay, so that's, weird. But then we go back. So let's do manganese. Where does the next electron go? Yeah, right? What would you rather do? Would you rather have a full and a half-filled, or a disrupted from half-filled and a half-filled, right? Like the first one's way better. Okay. So yeah, it fills up the 4s again, and then what? Yeah. So 3d. Okay, keep going. Because now we're going to get to the same question, right? We're going to get to the same spot where I'm going to claim that there is 4 or really 9 electrons. Is it going to stay like that? That's the next one, right? So wait, let me just kind of catch up with what I've written here. So and who are these? These are nickel and copper and zinc, right? Nickel, copper, and zinc. Okay. Okay. So the 4s 3d9, what you're claiming is that this is going to sit here with 2 there, and these are all like this, and that one is empty, right? Yeah. Well, no, the electrons know what they want. It's the problem is the 4s and the 3d are too close that it does this weird thing, right? So this is actually like, you know, proof that they're close enough, because, and that the s and the p are not close enough, because they don't do this thing when it's close, right? Like when it's like this, that electron doesn't jump up there. It doesn't happen. Yeah, it's because these two are so close in energy that it can make this jump. Okay, and it does the same thing. So again, it's not this here. Instead, we see this. What is it instead? Oh. 4s1 and 3d10. Yeah, exactly. Okay. Okay. Yeah, like 4 and like remember, when you're a 4s and you're like still the valence shell, you're kind of like, you know, and this goes for everything, I guess. When you're still the valence shell, nothing's been kind of like solidified yet, right? So you're still you can still be kind of like, your electrons aren't permanent. Your electrons can still be stolen and stuff, right? Whereas the electrons in the inner shell, those ones can't be stolen, right? Until you at least get rid of the valence ones, right? Okay, so sorry, I'm just resharing here. Can you see that okay? Okay. So yeah, instead we're going to see 4s1, 3d10. Okay, and then what about zinc? Yeah, like it has to go back into the 4s if you just, it's the only spot left, right? Okay, so we see some weird jumping, right? So let me kind of like label both of these actually as just kind of like our one and the other. So this is, who is this? This is nickel. No, this is copper. Jumping from 4s2 3d9 to 4s1 3d10, right? Which is more stable. And you should be able to kind of say it's Huns rule that says that this is more stable. Okay. And then this is cobalt. Cobalt jumping from 4s 2 3d4 to 4s2, no, 4s1 3d5. Okay, cool. Okay, so I think we're pretty much ready to kind of just talk quantum numbers and see how that's related to this. Okay. And you can pretty much now tell me the location of any electron according to its quantum numbers. Okay? Okay. So, quantum numbers. Quantum numbers. Your n is your principal quantum number, and it's your shell number. Right? It's the number out front of your, like, your 2s, the 2 is the n. Yeah? Okay. L is the angular momentum. Oh, God, I forget the names of them. Okay? They have these, you know, terrible names. One of them is angular momentum. One of them is... okay. Let me just Yeah, the angular momentum. Okay, yeah. Sorry. So this is the angular momentum number. Okay, and this is the subshell. So if you're talking about the S, then L is 0. If you're talking about the P, then L is 1. If you're talking about the D, then L is 2. And if you're talking about the F, then L is 3. Okay? And so oftentimes when you're talking about the quantum numbers, you learn the rules of what's allowed based on the n value. Okay? So this is kind of like your chart, your big chart that covers what's allowed. Okay? And I'm going to come back to this in a second because this is like useless unless you know what the heck's going on. Okay. So ML is the magnetic number, okay, magnetic quantum number. And this is which orbital in the subshell. Okay, so if you're S, then they're only really possible for you to be 0. They're only really possible for you to be 1. Basically, 0 means 1. Okay? Yeah, so this doesn't really make sense in the S because there's only one spot, right? But in the P, you're going to now have to ask me which P orbital. That's what we mean. Which orbital in the subshell. Okay? So what this means, the way that this system works is a lot easier to see if I just show you like this. So the way that we draw the S's, basically the middle one is always 0. And if you're the only one in the orbital, then you're a 0, right? But the one that has 3, look, there's a -1 location, -1 location, and a +1 location, and a +1 location. Okay? So because this is the P subshell, right? This is a P subshell, then the ML value is plus or minus the L value, right? Like it's equal to 0 and then plus or minus 1. Well, no, not for the P subshell, right? But then, yes, for the D's, we're going to have a 0. We're going to have a +1. Then we're going to have a +2 and a -1 and a -2, right? So they're just sort of like location names that you give as a 1, a 2, a 3, or right? No, sorry. A -1, a -2, -1, right? And so generally you can use the middle one is 0. Okay, so for here, the ML value is 0, plus or minus 1, plus or minus 2, right? Yeah, for sure. Like this is the standard. It actually technically, like you can't tell me which one's which. You wouldn't really be able to tell me which one's the -2 spot and which one's the 0 spot because energetically they're entirely equivalent. The electron sees no difference between the X axis and the Y axis. Like that's what you're saying basically, is that the X axis is always chosen first. No, it's not. So this doesn't correlate to the order that they're it's sort of like saying these are addresses on the street. It says nothing about who moves in first. Okay. But it doesn't make sense, or it's not easy to understand if you're just talking about the S. So the ML is a lot easier to understand when we're talking about the P or we're talking about the D, right? What would the restrictions be on the F subshell? Yeah, plus or minus 3, right? And so there would be, that's why there's 7, right? Because there's 3 over here and then there's 0 in the middle. 3 over here and 0 in the middle. Okay? So that's where we get our 1, 3, 5, and 7. This is a nice system to get 1, 3, 5, 7. Okay? But honestly, that's all the MLs really are used for. That's why we use this weird system. That's why I'm upset that it's like, we invent this whole system and like, yeah, cool, this is a cool trick that like, yeah, but it's like, you know, we had all this understanding before we introduced all these crazy numbers. Okay. Yeah, yeah. Spin is just the up and the down of our, remember, our spinning electrons. Oh, that's I mean, that doesn't really have a reason. Just so that I can't give it a reason. It's just so that, like, it's plus and it's minus. It could be +7 and -7. It could be +20 and -20, as long as they were the same number, right? Yeah, yeah, that's it. That's it. Yeah. I think maybe the one thing I may give them is that, you know, that if it's a half, you're talking about the spin number. You can't talk about any of the others because all the other ones are whole numbers or integers, right? So there's at least that, okay? But MS is just your spin number, and it's just either up or down, so it's either positive a half or negative a half. Okay? Okay. So now, can you tell me the quantum number, all 4 quantum numbers of that electron? Yeah, let's do it. So, sorry. Got freaked out there. Okay, so what are the quantum numbers of this electron? Remember, every electron will have unique numbers. So what is its N value? What is its L value? What is its ML value? And what is its MS value? Beautiful. Beautiful. Okay, wait, look, something's up. Look, this ML, it goes plus or minus all the way up to our, this is our L value. Right? That's plus or minus L. And that's plus or minus L. Right? Yeah. But wait a second. Are there 6 spots there? Sorry, are there 5 spots there? That's -2 to +2, right? Something's up. This is not our L value. L equals 2 is not the P's. Like, this is the weird part. 0 for L is S. So that means P is L equals 1. Right? P is L equals 1. And now the way, this is the reason I asked you that, or the reason I sort of like brought that up about the plus or minus L, is because that's how you catch that mistake. Because it sounds like your intuition is going to tell you that S is 1, P is 2, right? Do this little test, right? 0 and then +1, -1, all the way until you get to L. So if we'd kept going, we would have gotten this, and that would have told you that you had 5 spots, in which case you're talking about the D orbital. So it's worth a check to see whether you're talking about the D or the P after you make this choice. Okay? Okay, cool. So then, back to this one, what about the ML? Now, remember, you have to choose. You have to tell me which address. So this may be the range of addresses that are on the street, but you have to tell me which address you're at. So you got to pick one number here. What is it? Which spot are you at? Yeah, the 0 spot. Exactly. And then MS. Beautiful. Okay. Yeah, it's not so bad, right? Let's just try one more. And then I got to get running here. Okay, so let's try this one here. Good. So even though it looks like it's in the 4, right? We know it's 3D. Okay, good. Good. Does it make sense that 0 + 1 + 2 and -1 -2, that should be 5 spots in the D orbital? Yeah, it does. Yeah. good. Okay, so then ML. Sure. And S, MS. Good. No, like you. In fact, like you're probably going to be presented with a question like this, where I sort of say, "Are these acceptable values?" And you have to tell me whether they make sense or not. Okay. So does this make sense? Is that okay? No, right? There's no, first of all, there is no L equals 4, right? F is as big as it goes, right? And these values can't be the same. This one has to be at least one less, right? But it doesn't have to be one less. It could be two less or three less or whatever, okay? Okay, cool. Does that feel like that's like, okay, now those are just numbers that are talking about specific spots, right? Okay, cool. Okay. Awesome. Love to hear it. Okay, cool. Yeah, I think honestly that's like the meat of everything. I just want to check. Oh yeah, double check or go back and look at your who is off bow, who's Hund, and who's Paulie. Basically, Paulie is the one that said everybody has a unique number, and that is what makes them unique. So we generally give Paulie the like 2 to an orbital rule, okay, an up and a down. Off bow is the one that says everybody has to be as low on the totem pole as possible. This is an off bow diagram, so they care about energy. So that's the off bow diagram. And then Hund is the one that said, this magical synergy of a full or half full orbital. Okay, or not orbital, but subshell. Okay, cool. Yeah. I would take, like, if you have one, take a practice test. Do you have one? If not, I can get you one. I think I have one for this. Please. Okay. Okay, let me see. I think I do have one.